first. This is a picture that shows the flue gas coming in into this absorber. And then over here is the stripper or the regenerator. Professor Palmer Singh has asked me to give you questions for an exam. Okay, so this diagram will be one of the questions on the exam. Okay. So the question will say, please draw the units necessary for separation by absorption. And you will draw an absorber, and you will draw a stripper, and you will show the flows coming in and out. And then you will get the correct answer. Repeat. Okay. The question will be, please draw the units necessary to describe carbon capture by absorption. And you will draw two cylinders, and you will label one of them the absorber, and you will show the flue gas coming in, and you will show pure nitrogen coming out, and the solvent and the carbon dioxide will go into the top of this unit, which you will call a stripper or a desorber, and you will show pure CO2 coming out the top and fresh solvent coming out the bottom. These are in the notes that Professor Singh has sent to you, but now you know it, okay? That's one of the questions on the file. We had talked about three types of separations and introduced the absorber first. And so then are these videos. So we talked about the inside view that showed you all the bubbles that Professor Smith did. We had an inside view of thermodynamic equations. And remember, there's a graph, y-axis and x-axis. The y-axis is the composition of the vapor. The x-axis is the composition of the fluid. The equilibrium line starts at 0, 0 and goes straight. And the operating line, which is the concentration of mass, is another straight line, and it's above the equilibrium line. And you use those two lines to draw triangles that represent the contact between the gas and the fluid in each one of those stages. It's a tool for doing absorption. So we saw all those. We did not look at this one. It's too boring for you, I think. But now we have two other short ones to watch. One is on solvent engineering. And someone on this side of the room had asked this question yesterday. Wouldn't it be really interesting to design solvents just for this purpose? So we'll talk a few minutes about that. And then my colleague from environmental science asked this lovely question, is what actually happens at the interface between the bubble and the fluid? And why is that important? And so we'll see a short video on that. So this should be just a few minutes. Okay? And Professor Singh also tells me that today we have to end exactly at 3:30 for some programmatic reasons. So we will end a little early today. I hope you're all okay with that. I know it's been a long day for you to see so many lectures. Yes, okay. So let's get right with it then, shall we? Let's go to solvents. And I will put the microphone on the speakers again. Let's turn the speakers on. You could all hear last time, I hope? Yeah. Oh, good. Okay. Here we go. On your mark. Get set. Go. Welcome to the Berkeley Lectures on Energy. I'm Jeff Reimer, and today we're going to be talking about absorption, and in particular the design of solvents to improve the absorption of CO2 from flue gas. I would like to speak about solvent design and 4 topics in particular. How CO2 reacts in water, the use of amines for improving the absorption of CO2 into water, some of the commercial solvents that are currently available, and then some exotic new ideas concerning enzymes on ionic liquids for capturing CO2. Let's begin by recalling that when we used water as an absorbent and did a McCabe-Thiele analysis, we found that there are about 33 stages required with an L/V ratio of 3,000 at 40 degrees C. That translates into about 1,100 gallons per second of water, clearly an unacceptable water use for such a process. This requires us to think very carefully about the design, and the McCabe-Thiele diagram affords an opportunity to realize that there is considerable room for improvement. So shown here on this diagram, here, y and x, the equilibrium line in blue, the operating line in black. This is a three-stage absorption column. What would happen if we changed the Henry's law constant so that the equilibrium line was shifted? For example, if we increase the slope of the equilibrium line, we recognize that we increase the number of stages required for a given separation. Conversely, if we decrease the slope of the equilibrium line, reducing the Henry's law coefficient, we are able to decrease the number of stages required. The key then towards optimizing our absorption process is to change the Henry's law coefficient such that the equilibrium line slope is smaller and thereby improve the process. How does one increase the solubility of CO2 in water? Towards that end, we have to examine some of the chemistry of CO2 in water. And in particular, we note that when CO2 dissolves in water, it can dissolve as a carbonate ion, a bicarbonate ion, or as carbonic acid. And the nature of these species and their distribution in water turns out to be very important. For example, we show here the Henry's law coefficient for CO2 dissolving into water. Here's CO2 in the gas phase in equilibrium with CO2 in the liquid phase. Previously, this is all we've considered with regard to CO2 in water. But in fact, if one takes into account the chemistries of carbonic acid, the bicarbonate ion, and other species, we recognize that there are many, many equilibria associated with CO2 in water. And the key is to understand the chemistry of these processes in order to design a new way to absorb CO2 into water. For example, if one calculates with these known equilibrium constants what the normalized concentration is of various species in water, on right here I show that as a function of pH, the carbonic acid, the bicarbonate, and the carbonate ions all vary in concentration according to the pH. In very acidic conditions, carbonic acid is favored, and in very basic conditions, the double anion is favored. This suggests then that one way to improve the absorption of CO2 in water is to change the pH. Let's examine for a minute what would happen if we increased the amount of hydroxide ion in the water solution, driving this equilibrium constant to favor the dissolution or the reaction of CO2 in water to this bicarbonate ion. One way to increase the concentration of CO2 in water is, of course, to add sodium hydroxide. And one advantage of sodium hydroxide is that when it dissolves in water, 1 molar of sodium hydroxide added produces 1 molar of hydroxide ions. If one does this, the net result of the reaction is to drive CO2 in the liquid phase towards sodium bicarbonate, and thereby improve the process by which we sequester CO2 from the gas to the water and then out as sodium bicarbonate. This seems like a lovely idea, except for the fact that the heat of absorption now associated with this reaction is over 90 kilojoules per mole of CO2. And the consequences are that when we consider regeneration of CO2 in the stripper, or the desorber shown here on the right, we recognize that all that heat of absorption must be overcome to drive CO2 out of the process. This means that using sodium hydroxide as a way to improve the capture of CO2 in water is likely to be energetically too difficult. This leads then to suggestions of other bases that might be included with water to help improve the process. The most common of which would be a primary amine, a secondary amine, or tertiary amine. Amines are shown here with this structure. There are 3 covalent bonds to a nitrogen, and the lone pair of the nitrogens shown here. A primary amine has 1 organic group and 2 protons. A secondary amine has 2 organic groups and 1 proton. And a tertiary amine has 3 organic groups on it. What kind of chemistries are afforded when we include amines with water in order to capture CO2? One of the most common and popularly used primary amines is monoethanol amine. The structure is shown here. This material was known in the time of bottoms as a way to improve the absorption of CO2 in the water. It is a weak base, and 1 molar monoethanol amine has a pH of about 11.7, which means that only 0.5% of the monoethanol amine is ionized, as shown on the bottom slide here. Monoethylamine is an effective addition and improves the process,
and let me show you how with the McCabe-Thiele diagrams. Here they are. On the upper left, you see the absorption column using water, as we've done earlier this semester, and here's the stripper using water as a solvent. If we now use 30% monoethanolamine in water, look at the difference. Far fewer stages for both the absorber and for the stripper. Monoethanolamine is indeed an effective solvent. It is, however, part of a class of materials, the primary and secondary amines. And these materials do have a significant heat of absorption, as shown here, on the order of 80 kilojoules per mole of CO2. However, this heat of absorption is tunable in the sense that the composition of R1 and R2 can be varied, and the chemistry allows some tunability of this particular heat of absorption. The chemistry of CO2 reacting with these amines in water is not straightforward, as shown here in this diagram. The chemistry of CO2 reacting with two of these primary or secondary amines results in the formation of a carbamate, shown here, as well as with proton transfer over to the second amine. This carbamate ion equilibrates with water to form the bicarbonate and regenerate the amine. The interesting thing about this process is that because of this equilibrium reaction between the carbamate and the bicarbonate, this means that for every mole of CO2, it takes on the order of 2 moles of amine, thereby decreasing the effectiveness of the use of an amine. The tertiary amine, however, affords another possibility. That heats of absorption are smaller, and they are tunable according to the chemistry of the functional groups, as shown here. And the chemistry of CO2 reaction with this amine is much more straightforward. The carbon dioxide, the tertiary amine, and water equilibrate with the bicarbonate ion and the protonated amine. And this means then that for every mole of CO2 absorbed, we need only 1 mole of amine. So the advantage of the tertiary amine is that it's far more effective in terms of its use of amines, and it has a low and tunable heat of absorption. The disadvantage is that the rates of reaction of CO2 with the tertiary amines tend to be slower than those for the primary and secondary amines. Issues then with amines are the following. First of all, because amines are chemically reactive substances, they sooner or later react with oxygen that's in the flue gas or sulfur dioxide and other impurities. And this means that the amines degrade over time and need to be replaced, adding to the cost of CO2 absorption. Amines are very reactive substances, and indeed they react with carbon steel, so the materials of construction for absorption and strippers have to be more expensive and are subject themselves to degradation. Perhaps the most significant and least well studied of these is the solvent emission and environmental pollution associated with the use of amines. In all amine processes, a certain fraction of the amines will slip or escape from the process during the course of absorption and stripping. That also requires that the amine be replaced, but it also means that the amines will be emitted as vapor, and to capture them requires yet another expensive and absorption process. By the way, there are commercial solvents that are used for CO2 capture. These commercial solvents were developed in the context of removing CO2 from natural gas to sweeten the so-called natural gas. And these solvents include, for example, Selexol here. And Selexol is a proprietary mixture of polyethylene glycols, shown here. Selexol is a solvent, not a chemically reactant, so CO2 dissolves in this material, and it has the advantage of no water wash to recover the solvent because they have very, very low vapor pressures. The disadvantage of these materials is that they tend to have a much higher viscosity, that is, they're thicker and more resistant to flow than water, and so the rates of mass transfer and the efficiency of the trays tend to be limited when using Selexol for CO2 absorption from a flue gas. Another solvent of choice is methanol. Pure methanol is often called the Rectisol process, and the advantage of this is that it's simple. One just uses methanol as a solvent. The disadvantage is that the methanol must be maintained at very low temperatures to keep its vapor pressure low, which means that it's both an expensive process in terms of energy consumption, and one must have to use stainless steel, in order to prevent corrosion and decay. Finally, there are some exotic and new interesting possible solvent designs that would improve the capture of CO2 from water or from flue gas itself. Carbonic anhydrase is an enzyme found naturally in nature. It catalyzes the reaction of CO2 and water, or the reaction of bicarbonate and protons to CO2 and water. Indeed, it is the carbonic anhydrase enzyme that allows you to remove CO2 from your bloodstream when you exhale. The exciting thing about carbonic anhydrase is that the rates of reaction with CO2 are really quite extraordinary. This slide shows, for example, the various bases that are used and the reaction rates associated with CO2. And you see, for example, monoethanolamine has a reaction rate on the order of 7,500 in these particular units. But look at the reaction rates for carbonic anhydrase. They are 10,000 to 1,000,000 reactions per second, which means that this enzyme is indeed a very effective catalyst for shuttling CO2 from vapor to water, or vice versa. The interesting thing about the carbonic anhydrase enzyme is that it contains a metal atom, in this particular case zinc. So it forms a class of materials known as metalloenzymes. This suggests that it may be possible to construct synthetic analogs to carbonic anhydrase that might function almost as well, yet not require such a fragile thing as an enzyme. And indeed, the issues associated with the use of carbonic anhydrase is that the operation of the absorption and stripper are at temperatures that are usually much higher than the stability temperatures for carbonic anhydrase. And of course, the trace chemicals and impurities in the water could deactivate and degrade the enzyme. Secondly, I'd like to mention another class of solvents that affords a very interesting opportunity for carbon capture, so-called ionic liquids. In this image, which I've taken from Wikipedia, you see a beaker that contains salt, more or less at room temperature. Ionic liquids are very interesting in that they, like sodium chloride, contain a cation and an anion, but in fact, because of the chemistry and structure of the cation and the anion, they actually are liquids at room temperature, even though they consist of the anion-cation structure. The advantage of such ionic liquids is that they have very, very low vapor pressure, so that they can be used without having to escape, without any of the solvent having to escape. Here's a class of ionic liquids made from these chemical structures for the cation and the anion. And the interesting research opportunity for ionic liquids is the nature of the R groups can tune quite exquisitely the solubility of CO2. In the lower left here, I show the mole fraction of CO2 dissolved as a function of the different R groups included in an ionic liquid based on this class of cations and this anion. And you see that the solubility varies considerably based on these chemical structures. And there are wonderful research opportunities for people who can imagine, devise, and synthesize such ionic liquids.
Time to think, pair, share. Talk with your neighbor. 90 seconds. Start. Okay then, now I need a volunteer, and the volunteer should be a student at this university whose last name starts with the letter S. That should be a really easy, there should be like lots of people volunteering. A student at this university whose last name starts with P. How about any student at this university? A question, an idea, or an extension. And there's no bad answers. There's no incorrect answers. I need to... Yes? 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 Ah, okay. So, of course, the answer I don't know, but I do know what you're getting at. So let me just say, there's this issue that's important in chemical and environmental sciences, which is sustainability. That is to say, when I use a product for carbon capture, how much CO2 do I generate in creating that product? So I'll give you a good example of this. When the Toyota Prius was introduced in the United States as a hybrid electric vehicle, the emissions from cars decreased dramatically because the mileage per gallon went way up. Initially, the cost of production of the batteries, energy-wise, and the car exceeded the return, exceeded the savings that would be available from the car. And so many people dismissed the notion of hybrid electric vehicles and electric vehicles for just this reason. And of course, Toyota, being a company that knows how to manufacture, recognized that if sales exceeded a certain threshold, the returns on manufacturing improvements would ultimately win. And in fact, the Prius is now a vehicle who actually saves CO2 and doesn't increase it. So your question, sir, is excellent. When we imagine salts such as ionic liquids, is a perfect example. These are exotic chemicals. They're not easy to synthesize. And for probably many generations of their use, the CO2 emitted in synthesizing them might exceed the amount that was saved. And that's a serious problem. Thank you for that comment. Sustainability. It's a really important subject that students should all learn. One more before we go on to mass transfer. Yes. Yeah, that's a great question. So the leaders in absorption chemistry believe that piperazine, which is an aromatic ring with a nitrogen on it, is the most effective. It has the lowest vapor pressure. It's cheap. It's readily available already. And they claim that that should be the gold standard by which all other technologies are compared. Piperazine, P-I-P-E-R-I, piperazine, Z-I-N-E, yeah? And you could look it up in Wikipedia. It's a nice chemical. So that seems to be a favorite of everyone. But it certainly is true that if you call up a company today to buy an absorber for your campus power plant, they will sell you monoethyleneamine in water, because that technology is already proven. Oh. Monoethyleneamine, why don't we use it? Is that what you said? Yeah, amines in general, the problem is they slip. That is to say, in the course of operating this unit, some of them vaporize and leave into the air, and they're typically not friendly to the environment. They're also expensive. Yeah. So. All right, let's go to the next one, shall we? No, it's a liquid at room temperature. We'll look it up. Let's look it up on your phone. Yeah, it's a liquid at room temperature. I'm pretty sure. Well, look. Let's look. Challenge me on that, okay? But you don't have internet here in the room. Oh, yeah? Okay. So while the next video, somebody sacrifices themselves and looks up the melting point of piperazine, okay? By the way, the piperazine would be dissolved in water. Yeah, yeah, solution of piperazine. All set? Here we go.
Welcome to the Berkeley Lectures on Energy. I'm Jeff Reimer, and today we're going to continue our discussions of absorption for the use of capturing CO2 from the exhaust gas of power plants. In today's short video, I wish to consider effects beyond equilibrium thermodynamics on the design and analysis of these systems, and in particular what role mass transfer plays in our absorbers and strippers, how chemical reactions affect those mass transfers, and then finally a return to the notions of solvent design for capturing CO2 with these processes. Recall that when we were considering the McCabe-Thiele analysis for design of absorbers up in the upper left, I had an equilibrium line in blue, an operating line, and stages stepped off. And in order to achieve the most effective design, I had to empirically shift the equilibrium line over as shown here in green. Similarly for the stripper, using the Henry's law coefficient for the equilibrium line in the stripper was in fact not the most accurate way to conduct the design. In fact, I had to empirically adjust the equilibrium line in order to best match practice. How am I to understand what these effects are, and what do they do to, and can they be thought of in terms of solvent design? In order to understand more deeply what's happening at the absorption plate, I return to this image here. Here's a cartoon of the absorber column. Here's a picture of an actual plate. And recall that fluid descends from above, gas rises from below, and we have this froth or vapor, intimate vapor-liquid contact occurring inside the absorption column. In order to understand the effects of mass transfer, I first need to look very, very carefully at the interface between the vapor and liquid phase. In this cartoon I've taken from Wikipedia, I show a bubble in a fluid. And in particular, I want to understand the concentration of CO2 inside the bubble as it goes across the interface of the bubble and into the bulk liquid. So here's a graph in which I imagine that. Here's concentration on the y-axis, position on the x-axis, and deep inside the bubble, near the origin here, I have the concentration of CO2 in the gas phase. Deep inside the liquid, over here on this diagram, I have the concentration of CO2 in the bulk liquid. And I imagine then that there's a change in CO2 concentration from the gas phase value to the bulk liquid value, and that change occurs over a thin film interface. And I want to know the effects of this thin film interface on the design of my column. It turns out there's a great truth that's easily derived in chemical engineering, that rate processes are usually given by a geometry, a famous number you find in textbooks, and a driving force. How does that apply to this particular situation where, for example, I have gas on the left side and I have CO2 in the gas phase on the left side of the diagram and CO2 in the liquid phase on the right side of the diagram? I recognize that across this liquid film, as shown here, there's a rate, that is, there's a flux of CO2 across that interface. That flux would have dimensions, for example, of moles of CO2 per area per time. That's a rate process. And the great truth from chemical engineering can be expressed like so, namely that the flux of CO2 across that interface is given by 1 over the thickness of the interface, a diffusion coefficient for CO2 in that liquid film, and a driving force, that is the difference in concentration between CO2 in the gas phase and the concentration of CO2 at the film-liquid interface. I can rewrite that expression as the flux of CO2 across the film as being given by a mass transfer coefficient times a concentration difference as shown here. That can be rearranged easily to show that the concentration of CO2 at the film-liquid interface is in fact the gas phase value minus a flux divided by a mass transfer coefficient. And it's this particular expression that can be mapped onto the McCabe-Thiele diagram to show us why mass transfer affects the equilibrium line choice. Here, for example, is a schematic of a McCabe-Thiele diagram, equilibrium line shown in green, Henry's law, and the operating line shown in red. And of course here is a stage one might step off for a situation in which CO